we'll speak about symmetry protected topological phases and beyond. Please.
Okay, well, as you just heard, I'll be telling you about SPT phases and what lies beyond SPT phases today. But before jumping into that, let me take a moment and thank the organizers for making this all possible. It's been really nice the last week and a half to have those spontaneous lunch table exchange of ideas that can't happen over Zoom. And it's been great hearing the last week and a half of talks. No. Should I point this somewhere? Ah, okay, it's backwards. Yeah, I see. Okay. Well, so for those of you who attended last week's review talk, you should recognize this first slide as a screen cap of Shinsei's first slide. I thought I couldn't beat this diagram, and I wanted to put the scope of today's talk in the context of last week's talk. So both talks are on phases of matter. Both talks are on phases of matter that are disordered with respect to symmetry breaking, yet have some other more exotic type of quantum order. Both are on gapped phases, but where the fork occurs is between topological order and no topological order. So last week, Shinsei told us mostly about topologically ordered phases, but today I'll talk about those that are trivial or almost trivial with respect to topology, yet become quite interesting when enriched with symmetry. So I recognize that there's quite a variety of backgrounds of people in the audience. So I hope that most of the talk makes sense to people who don't have a lot of exposure to these ideas, yet I've also tried to throw in bits that are interesting to everyone in the audience. I've also included references whenever possible, so if you find a particular idea interesting, hopefully those will come in handy for learning more. So an outline, the talk is roughly split up into 4 pieces. The first is on entanglement and gap systems. I'll tell you a little bit about area laws, tensor network methods. These things are tools that'll be useful in the rest of the talk. Then I'll get into some definitions of invertible phases and SPTs, some properties of how to characterize them, anomalies, etc. I'll then move on to detecting invertible phases with non-local order parameters, and I'll close with a small section on free fermionic phases. I just added this last section recently after hearing Christopher's nice introduction to the K-theory periodic table, and I thought I'd try to make a connection between that classification of free phases and what I'll say here about interacting phases. Okay, so first, entanglement and gap systems. The systems I'll be working with today are lattice systems. So the Hilbert space is a tensor product of local Hilbert spaces attached to the vertices of a lattice. The Hamiltonians will always be local, which means that they're a sum of terms defined on some small regions of the lattice. I'll also assume translation invariance, which means that the local Hilbert space and the Hamiltonian terms don't depend on their location in the lattice. For a lot of the results, translation invariance isn't strictly necessary. They hold without it, but for the tensor network claims in particular, they're significantly more technical without this assumption. So just keep it in mind in the back of your head. Now, notice that this data of the local Hilbert space and the local terms of the Hamiltonian don't make reference to a particular lattice. They actually define a family of systems. Given a lattice, you can make sense of this data and construct a total Hamiltonian on that lattice. And that's actually crucial for defining what it means to be gapped. On a particular lattice, when your on-site Hilbert spaces are finite dimensional, your total Hilbert space is finite dimensional, and so the spectrum just trivially has an energy gap. But when we have this family of systems going out to infinitely large systems, it's possible to talk about gap systems defined as those that have an energy gap between the ground state and the first excited state that persists in the thermodynamic limit. So gapped ground states turn out to be very special states. So they're thought to have an area law for entanglement entropy. In one dimension, this is a hard result that was proved by Hastings and proved later on. In 2 dimensions, it's not quite as straightforward, but at least for the topologically ordered states, including the trivially topologically ordered states that I'll talk about today, there's also an area law modulo a constant term. So this came up in last week's review talk, but just a quick refresher. To define entanglement entropy, take your system with the ground state on it, split it into 2 regions, trace out the degrees of freedom on region B. You're left with a density matrix on region A, and now take the entropy of it. The claim, which is called an area law, is that this quantity scales like the size of the area of the boundary between regions A and B. So in this picture here, it's the length of the perimeter because we're working in 2 dimensions. So the fact that there is an area law for these gapped ground states suggests that entanglement is somewhat short-ranged. We can picture the entanglement between region A and region B as coming from a bunch of bell pairs that stretch across the boundary between the 2 regions. Note that a generic state in the Hilbert space does not have that property. You could have entanglement between some point in the bulk of region A and some very far away point in the bulk of region B. But for gapped ground states, since the entanglement entropy is scaling like the perimeter of that boundary line, these are the only bell pairs that contribute. That's just a little intuitive picture. So given that these ground states are very special, one might hope that they have a neater description. The total Hilbert space is huge. The number of, like, the coefficients in your wave function grow exponentially with the system size. But for gapped ground states, turns out we can do a little better. So to say what I mean by doing a little better, let me first establish some notation. Tensor networks will appear in a few places in this talk. Oftentimes it's possible to make an argument without tensor networks, and I'll do that in parallel to the tensor network argument, but I think it adds something to use these tools. So what is a tensor? A tensor is just an n-dimensional array of numbers. We draw it diagrammatically as a vertex with a bunch of legs emanating from it, one for each of these dimensions of the array. And there are manipulations we can perform on tensors to build new tensors. So we do this by tensor contraction. If you form a diagram of multiple tensors and some of those legs end up internal, they're summed over. The indices are summed over, just like in a Feynman diagram. So for example, on the left, I've drawn the diagram of the trace of the matrix A. A is a matrix because it's just a 2-dimensional array. And on the right, I've drawn matrix multiplication of A and B. Okay, so that's the basic idea behind tensor networks. And this makes discussing these tensor network states a lot easier. In 1 dimension, let's see what special form gap states, ground states of gapped Hamiltonians can take. To do that, we start with a state drawn on the left. Its wave function is just an array of numbers. There's one of these legs for every site in the lattice. Perform a Schmidt decomposition on the state. So separate the leftmost leg from the rest of the system. Diagrammatically, it looks like what I've drawn on the right of the equality. if you repeat this process, you split up the state into just a bunch of blocks. And then if we combine the Schmidt eigenvalues lambda with this block, which I haven't given a name, we get a new tensor A, and that's the tensor of the matrix product state. So we've essentially rewritten the state as a product of a bunch of these tensors A. So for a fixed index I on the physical leg, AI is a matrix of rank D, which is called the bond dimension. So D has something to do with the entanglement of the state. So for example, it can be recovered as the zeroth Renyi entropy of the state. Explicitly, the wave function is given just by a product of matrices, hence the name matrix product state. So on a closed chain, you have a product of matrices, and then you need to close the chain by connecting the last site to the first site, and that amounts to summing over that last index, so performing the trace. On an open chain, it's very similar, except we have boundary states. So the neat thing about matrix product states is that they can be represented with a much fewer number of coefficients than a general state in the Hilbert space. So that scales with linearly in the number of sites as opposed to exponentially. Okay, so as I was saying, the bond dimension D to represent a generic state on n sites grows exponentially in n. But ground states of gapped Hamiltonians have a special entanglement properties, and as a result, they can be approximated with matrix product states that have a finite bond dimension D. So what it means for D to be finite is that if I try to cut out region A from region B, I'm cutting through bonds of some finite dimension. So that kind of puts an upper bound on the entanglement entropy between a region and its exterior, reflecting the area law. We can actually throw out this factor of n in the number of coefficients in the matrix product state by using translation invariance. We can always take the MPS tensor to just be independent of the site. So far I've talked about how ground states of gapped Hamiltonians can be represented by matrix product states, but there's somewhat of a converse to this statement. Namely, given an MPS state, there is a parent Hamiltonian whose ground state is that MPS state. So in nice situations, when we have translation invariance, this Hamiltonian is gapped. It has a ground state degeneracy that's constant in the system size, and it's a local Hamiltonian. So we can sort of think of matrix product states and ground states of gapped Hamiltonian as interchangeable. So a few more facts about MPS. The MPS representation of a state is not unique. There can be multiple tensors that define the same state. This is a sort of gauge freedom. It can be partially fixed by putting the state, the tensor in a canonical form. There's still it's a partial gauge fixing, so there's some remaining gauge freedom, but it just amounts to conjugation of the tensor by a unitary matrix. So what do I mean by canonical form? Well, one can form the transfer matrix of the MPS state with the diagram here on the left. E equals this thing that consists of the tensor A and A dagger. Canonical form means that the identity is a left fixed point of this transfer matrix. So that's the diagram in the middle. The identity is just this straight line on the left side that connects the top left to the bottom left leg. And the diagram is showing that it's an eigenstate of eigenvalue 1. Injectivity is another useful condition, which says that this identity is the unique fixed point of the transfer matrix. And it implies that there's a unique right fixed point called rho, and drawn as a purple square. which is full rank. Okay, so now let's try to put these tools to use. So you may have heard before that correlators in a gap system have the property of being exponentially decaying. In the language of matrix product states, this is very easy to see. In fact, they are sometimes called finitely correlated states because they have this property. So on the top, we start with the expectation value of two spatially separated operators. So it's the expectation value because the MPS is drawn at the bottom, the bra for the MPS is drawn at the top, and we're contracting them together with the operators in orange sandwiched in the middle. If we apply what I just said, if we apply the injectivity condition, all of this infinitely many copies of the transfer matrix that we have outside of these operators disappear and can be replaced by some states L and R. And so we're left with this J, the distance between the sites, copies of the transfer matrix sandwiched in between states L and R. And that tells you that whatever the second highest eigenvalue of this transfer matrix is, controls the exponential decay of the correlator. Now, matrix product states have another description, which is useful because this is a description that can be generalized to higher dimensions. This description is called PEPS, which means projected entangled pair states. So the ingredients for a PEPS are, again, some physical Hilbert space, some virtual Hilbert space, also called the entanglement space, and some tensor, which links them together. So the construction is to take maximally entangled pairs on the edges of the lattice. So these pairs live in a copy of the virtual space and its dual. And the pairs come together at the vertices. And then the vertices are hit by the conjugate of the MPS tensor, A dagger. So when you put that all together, the result is exactly the wave function I showed you before. It's the MPS state. So in higher dimensions, there are also PEPs. One takes a lattice, puts these maximally entangled states on the edges, and then when they come together at vertices, one projects down and that binds them together. PEPs are nice because they manifestly have an area law just for MPS. So if I try to cut this region out from the exterior region, I have to cut through these virtual legs. And these virtual legs have some finite bond dimension. And so that puts an upper bound on the amount of entanglement between the inside and the outside of the region. Okay, so that was kind of an introduction on gapped ground states, and it should set the groundwork for talking about phases of matter, which is the main purpose of the talk. I can pause here for a second if there are any questions about what I've covered so far. Okay, so I'll carry on then. Okay, so gapped phases. To define a gapped phase as an equivalence class of gapped systems, one has to first define an ancilla. So an ancilla is just the least interesting Hamiltonian. It has a bunch of local terms defined on site, and these have unique ground state, and the ground state is a product state. With this in mind, phase equivalence can be defined as saying that two systems are in the same phase if they're related by appending ancillas, which means stacking the system with an ancilla system, and then smoothly deforming without closing the gap. So I want to make a comment here to connect with something that came up in one of the talks last week. There are things called fragile phases where one just considers smooth deformations without adding ancillas. So in particular, if a state is fragile, it could be destroyed by adding ancillas, but I won't get into those here. So the intuition for this definition is that observables suffer discontinuities when there's a degeneracy in the spectrum. So for example, when the gap closes. So if you can do a deformation without causing something like that, then qualitatively your systems are in the same phase. Yeah.
Thanks. So just to make sure, are you saying that if I gave you a Hamiltonian with some couplings and then try to draw a phase diagram based on scanning these couplings, you would say it's not really a properly defined phase if I say, oh, there's a confinement on this side and I don't know, deconfinement on the other side or something, because I haven't taken into account the possibility that adding ancillas will ruin these phases?
Yeah, that if you have if you're talking about lattice systems,
For instance,
if you're talking about field theories, then what counts as an ancilla is less obvious. But yeah, so there are like these. They came up in the talk last week, like these 2-band Hopf insulators, which they have a non-trivial band structure. You can't deform it to a trivial one. But as soon as you add additional bands on top of those 2 bands, there are deformations which trivialize it. Yeah.
Okay, thanks.
Okay. So thinking about deformation classes of Hamiltonians is sometimes not the most convenient thing to do. So there are some results which show that there's an equivalent way to talk about phase equivalence. 2 states are said to be in the same phase if, after appending ancillas, we can evolve them into each other by a local quantum circuit of low depth. So by local quantum circuit, I mean what's drawn here. There are, it's acting from bottom to top by these gates, which act on 2 sites at a time. The gates come together in non-overlapping, they don't overlap with each other within a layer, and then they're stacked layer after layer. Crucially, the circuit needs to be low depth. If you could have whatever depth you want, then you can just simulate any unitary. You can relate any 2 states to each other. But if the depth of the circuit grows slowly enough, I think technically it needs to grow at a polylog rate in the size of the system, then it gives you a meaningful notion of phase equivalence, which corresponds to the definition on the previous slide. Okay, so let's use what we know so far to show the most basic thing, which is that there are no non-trivial phases in 1 dimension. So there's a nice argument from matrix product states. So after blocking the system k times, the new transfer matrix e to the k looks like a projector between the 2 fixed points, 1 and rho, up to some corrections, which are of the size, the second highest eigenvalue of the transfer matrix. So the transfer matrix just looks like this diagram here, E equals this projector. This means the MPS state itself can be written in terms of square root of rho. And then this state is simple to disentangle. One just uses a circuit of these pink gates, and the gates just need to satisfy this property on the left, which is that they take the square root of rho and they disentangle it into a product state. When you act on the entire state of the system with that gate, you're left with a product state. So what we've just done is taken a generic 1-dimensional state and disentangled it with a circuit, and that shows that it's in the same phase as the product state, so it's in the trivial phase. Now, this is a very different situation from 2 dimensions where there are many non-trivial phases, such as string net models. And these string net models have tensor network descriptions, but an argument like this doesn't hold. They can't be disentangled to a product state. Okay, so a nice thing about systems and phases is that they can be stacked together. It's not just a set of phases, there's an additional algebraic structure on the set of phases. So to stack 2 systems, A plus B equals C, we take the Hamiltonian of A times the identity, and we add it to the identity tensor, the Hamiltonian of B. That's the Hamiltonian of the new system. The Hilbert space of the new system is just the tensor product. So this operation on systems is clearly commutative, doesn't matter which order we add things. The ground state degeneracy is multiplicative, but crucially, stacking is compatible with phase equivalence. So if system A and A prime are in the same phase, B and B prime are in the same phase, this implies that the stack of A and B is in the same phase as the stack of A prime and B prime. So as a result, these equivalence classes we've just defined, which I'm denoting by bracket A, for example, the equivalence classes themselves can be stacked together. Was that a question? Okay. Okay, so there's one phase in particular called the trivial phase. This is the one that contains the product state or the ancilla, and it's the unit of stacking. If you stack it with any other phase, you get back the phase itself. This allows us to define invertible phases as those that have inverses. So an A is invertible if there exists an A prime such that when I stack the 2 together, the result is a system in the trivial phase. So because of invertibility, the set of invertible phases has the structure of an abelian group. And again, it's abelian because the stacking operation is commutative. So phases as a whole don't have this nice group structure, but if we strict to invertible phases, they do form an abelian group. So invertible states are almost trivial because of what I told you on the last slide about how ground state degeneracy is multiplicative. We see that invertible states have a non-degenerate ground state. Once you have ground state degeneracy, there's nothing you can multiply it by to get back down to 1. So in 2 plus 1D, lack of ground state degeneracy means that your topological order can't have any bulk anionic excitations. But despite these phases being almost trivial, they can have non-trivial, by which I mean anomalous, boundary physics. They can have non-trivial responses to gauge and gravitational probes. Because they're almost trivial, they're sometimes called short range entangled phases, but this is a bit of a misnomer because just by definition, they can't be disentangled by circuits. So their entanglement is not entirely short ranged. Like the most basic example of an invertible topological phase is the Kitaev chain, and it has like a non-trivial topological entanglement entropy. So it's sort of long range entangled in that sense. So despite these being trivial, they really do exist. For bosonic phases, the simplest example occurs in 2 plus 1 dimensions. So it's this bosonic E8 state. There are, of course, a bunch of non-trivial bosonic states with various central charges, and having a non-trivial central charge indicates that you're not in the trivial phase, but most of these are non-invertible. The special thing about the E8 state is that it has no bulk anionic excitations, yet it still has a non-trivial central charge. In fermionic systems, we get a lot more examples. So 1D and 2D have P plus IP superconductors. The 1D example being the Kitaev-Majorana chain. These are invertible topological orders. Actually, all systems of free fermions, so non-interacting fermions, are invertible. This is not all phases of invertible fermions. There are some that need interactions to exist, but at least all free fermionic systems are invertible. And I'll talk more about them later.
So for you, the Kitaev chain is an invertible phase.
Yes.
Okay.
Yes. Okay, so we just classified we classified all phases, including invertible phases, in 1 dimensions for bosonic systems, but to do it in any dimensions, and once you include fermions and symmetries like time reversal, it becomes quite a hard problem. So the classification is only conjectural. It sort of looks like this periodic table of topological insulators, except the values in the table are different. And this conjectural classification has several motivations. It can come from classifying what topological actions are possible to write down. It can come from topological field theories. There are generalized cohomology arguments that suggest that this is the right classification. But actually showing on a lattice that you have these equivalence classes of states, which are grouped together based on whether they can be connected by a low depth circuit, is actually a hard problem. And there are some open questions in that area. Okay. Yeah.
Just to be sure I understood, so an invertible state is a gap state, which I can find for that state another state when I add them together, or I
Stack them.
together. I get something which is a matrix product state. Is that correct?
Which is a product state.
Oh, which is
Yeah.
a product state.
Yeah.
Okay, is a trivial product state.
Is it? Yeah.
And so you said the Kitaev chain, the 1D Kitaev chain, is an invertible
Mhm.
state. What is the thing that I stack
Yeah, that's a
just
great
to
question.
get an more physical intuition?
Yeah, so the Kitaev chain, its inverse is itself. So the Kitaev chain has these dangling Majorana modes at the end, some anomalous boundary behavior. And if you stack 2 copies of the Kitaev chain, now you have 2 Majoranas at the end, and you can couple these together. Even a quadratic term is enough to couple them together, and that gets rid of the anomaly on the boundary. And at that point, you can connect it to a product state.
Okay. And just another question to clarify, whenever you're referring to something trivial,
Yeah.
you're thinking in the sense that there's no topological order. Is that what you're like? No deconfined excitations and so on. Is that what you're saying with, and then adding the definitions you just mentioned of invertible states? Is that correct? Or
I guess when I say trivial, I mean something even more trivial than the lack of anionic excitations. I mean that it's actually in the same phase as a product state.
okay, so okay.
The Kitaev chain has no bulk excitations. It's the only thing non-trivial about it is these dangling Majorana modes at the ends. Yet it's non-trivial in the sense that I'm using it. Yeah.
Okay. Thanks.
Hi. When you refer to states and you describe states and you use circuits, you're always referring to a special basis, which is the basis in which you define your locality or your Hamiltonian, your sites. Is it correct? I mean, for example, you say that you can deform a state is trivial if it can be written as a product state.
Mhm.
but that implies that you have a special basis in mind.
Yes, right. It's
So everything is from the beginning because you define a lattice, and
Exactly.
that's everything is in reference to this lattice and this basis.
yes. So if you forget locality, then just everything becomes trivial.
Yeah.
Yeah, there's no topology without locality. Okay, so next, what I want to do is make these invertible phases slightly more interesting by enriching them with symmetry. So one can consider more exotic symmetries, but for the purpose of this talk, let's have our global symmetry act on site. So that means it's just a tensor product of local actions. Then we do two things. One, we restrict to symmetric systems. If the system is not symmetric, we throw it out. And then secondly, we take this space of symmetric systems, and then we define a new equivalence relation on it, which is that two systems are in the same phase if they're related by a symmetric path. So you can symmetrically deform from one to the other. And this deformation notion of phase equivalence, once again, has an interpretation in terms of circuits. It's the same as what I drew before, except now the gates of the circuit are individually symmetric. So crucially, the individual gates of the circuit are symmetric. It's not enough to say that the circuit as a whole is symmetric. There's some recent work that shows that these globally symmetric circuits actually can disentangle not all, but many phases that would otherwise be non-trivial. Okay, so I'm calling these equivalence classes symmetry enriched phases or G enriched phases. They can also be stacked together in the same way. So when you perform this operation on the Hamiltonians, you get something that's not only gapped, but once again symmetric. And moreover, G enrichments of invertible topological orders are themselves invertible. So if I took an invertible topological order and then it got split up into a bunch of smaller equivalence classes based on whether you can deform between parts of it by a symmetric deformation, each of those smaller classes would also be invertible. And so these G-enriched phases, again, form an abelian group. Symmetry enrichments of the trivial phase are a special case, and they're called symmetry-protected topological phases or symmetry-protected trivial phases, depending on who you ask. The name symmetry-protected trivial comes from the fact that if you get rid of the symmetry, then it really is trivial because it was an enrichment of the trivial phase. So the symmetry is doing the protecting of the phase from being trivial. These are not all G-enriched invertible phases. They're a subset, but I'll denote them by SPT. And here D is the dimension, G is the symmetry group. Now, a further subset of these phases are characterized by group cohomology. They're called group cohomology SPT phases. But there are other SPT phases outside of group cohomology, which are known as beyond cohomology SPT phases. Yeah, so most authors say SPT stands for symmetry protected topological. The term symmetry protected trivial is used by some and is maybe, in my opinion, the better term because there's actually nothing they're topologically trivial. The only thing non-trivial about them is the interplay between the symmetry and the entanglement. Yeah. Yes. Yes. So by trivial, I mean that it's connected to a product state. So this is more severe than a lack of bulk excitations. By symmetry protected trivial, I mean it would be trivial if not for the symmetry. They are non-trivial. No, I meant that they are not non-trivial as topological phases. Yeah. No, so that's the other definition of being non-trivial. So these invertible states, and I'll get into this later, you can put them on non-trivial topologies and they're still non-degenerate, despite them being non-trivial in that they're disconnected from the product state by a deformation. Yeah.
They're trivial and trivially connected to a product state,
Right.
In a local basis, then what does the symmetry, like why does this symmetry enriching cause them to be interesting? Just that there is some symmetry that if I have any perturbation that respects that symmetry and does not close the gap, I will not get out of the phase. Is that
exactly? So
okay?
So if I'm in a non-trivial SPT, then if I follow any deformation at all, I can find one that will get me to a product state. Or if I apply any local circuit at all, then I can get to a product state. But if I restrict myself to symmetric deformations or symmetric circuits, then I'm non-trivial. Yeah.
Okay, thanks.
So in this context, when you consider fermionic systems, for example, the Kitaev chain, the Z2 global symmetry of the Kitaev chain is inside your symmetries here, or you're considering just bosonic phases here?
So on this slide, I have in mind bosonic phases, but I'll talk about fermionic phases as well later on. Yeah. Yeah, in this talk, I'm only going to consider the case where you have the Z2 fermion parity symmetry times some internal symmetry G, but of course, more generally, you could have a full fermionic symmetry group with a Z2 symmetry embedded inside. Yeah. Okay. So let's talk a bit about what these group cohomology phases are, what they mean physically. And the way to do that is to think about anomalies. So as I mentioned before, these phases are almost trivial and that there's nothing happening in the bulk, yet they're not trivial because there's something exotic happening on the boundary. And that exotic behavior on the boundary is known as anomaly. So anomalies come in different types, but for group cohomology phases, this is how it works. In one dimension, the cohomology invariant captures symmetry fractionalization. So if I act on the boundary of my one-dimensional system, so that boundary consists of two sites, that action needs to be a linear representation of the symmetry. But then if I look at just one half of the boundary, so one of these points, it's no longer important that that be linear, because if I have some phase on one side, it's canceled by the phase on the other side. So the boundary action of the symmetry, which I'm calling VG, can be projective. And a projective representation is one that satisfies the group composition law up to some phase omega. So that's some U1 valued thing that takes as arguments 2 group elements. Now, if I act with G, H, and K group elements, and I do this in 2 different ways and require that they're equal by just associativity of multiplying these matrices VG, this gives you some constraint on these phases omega, and this constraint is known as the 2 cocycle condition. So it's written here, oops. So it's written here, and another name for this is that the co-boundary of omega is equal to 1. Also, we can freely redefine the boundary action V by some other phase beta. Why can we freely define it? Because again, we only need to reconstruct like if we have a phase in VG, it's canceled by the phase on the other side of the boundary. So in total, we get the same symmetry action on the total boundary. So if we perform this shift, it gives you a shift on omega. And the result is this new thing, omega times co-boundary of beta. So the set of omegas satisfying the 2 cocycle condition modulo this freedom beta is what is called the cohomology group. So it's the second cohomology group of G with coefficients in U1. So this was kind of a nice intuitive argument, thinking about symmetry fractionalization without dealing with the lattice or anything like that. But historically, it's not.
Should I consider the Kitaev chain as an example of this or not?
The Kitaev chain behaves very similarly, but it's not quite this. Because the Kitaev chain doesn't need symmetry to be protected. Well, it needs the fermionic superselection rule, but there's actually no projective symmetry happening there.
Okay.
So for the Kitaev chain, you have a Z2 fermion parity, but Z2 fermion parity has no projective representations. So there's no way to get an omega that is non-trivial.
So I have to keep in mind an example in bosonic theory.
So the example to keep in mind is symmetry group Z2 cross Z2. And the phase, so you have 2 phases there because second group cohomology of Z2 cross Z2 is Z2. There's a trivial phase and there's the Haldane phase, which includes like the AKLT state.
Okay.
Yeah.
Thank you.
Yeah. So I guess originally this sort of extraction of the cohomology invariant came from other sources like using matrix product states or classifying topological fixed points. Depending on who you ask, this was not truly made rigorous until recently when people thought about actually infinite systems instead of just families of finite systems. So this argument in the C-star algebra formalism was worked out in 2018 and 2020, and the results agree. Again, there's an invariant given by second group cohomology. So I mentioned before that we would be putting these tensor network methods to use. I think this is a nice alternate perspective on symmetry fractionalization. So now symmetry acts on the state. It being symmetric means that UG on the state equals the state itself. Now let's represent both sides of those equations with an MPS. The tensor for the state psi is AI. The tensor for the state UG psi is UGA. And since they define the same state, they must be related by a gauge transformation. So we have this relation here on the MPS tensor. So diagrammatically, it looks like this. You're hitting the physical leg with UG, and the result is that on the entanglement or virtual spaces, you're getting this projective action VG. And there's also an overall phase. So VG is exactly what we had in the other picture. There is this extra phase here, which is kind of an artifact of us dealing with translation invariant matrix product states. So we can basically ignore it for now, but I'll make a small comment. Whenever you impose not just the on-site symmetry, but also a translation invariant symmetry, you get, in addition to the normal invariants, which are called strong invariants, you get weak invariants as well. The invariants are weak because they get washed out as soon as you forget about the translation invariants, as soon as you allow deformations that break translation invariants. And weak invariants are interesting in that they are the strong invariants of lower dimensional phases. So basically what's happening here is that there's a 0-dimensional SPT phase, which is just a charged state on each side in the lattice. And normally these get mixed together and washed out, but because we have translation invariants, there's just this 0-dimensional SPT phase stuck on each side of the lattice. And the charge of that state is what's giving this e to the I theta. Let's see, trying to remember. I think if no one's in need of a break, probably 10 minutes from now, I'll get to a good stopping point for if. Yeah, that would be more natural, but up to you. Okay. Yeah, right. So
What is the upshot of the previous transparency?
it's just it's an alternate argument.
What do I see? Fractionalization.
Well, so you get this given a state and an action of the symmetry on the state, you get matrices VG, and these VGs form a projective representation, which has a cocycle. So this is a way of extracting the topological invariant from the state and the symmetry action on it. Yeah. Okay, so there's a version of this argument that works in higher dimensions. Let's see how it plays out in 2 dimensions. So G now acts on the boundary of this 2-dimensional bulk as some operator VG. So the bulk is this purple block. The boundary is this blue line, and VG is the thing that acts on all of it. Now let's restrict the action of VG to a region M of the boundary. So we get some operator VGM. The group law for VGM only needs to hold up to some operator omega, which is defined on the boundary of the region, so the 2 dots. Why does it only need to hold up to that operator? Because we really care about the entire VG being well-defined, and this operator is just going to get canceled when we take VGM and VGM complement. So it's allowed to be there. Associativity of VGM means that this operator omega satisfies a relation that looks kind of like the 2 cocycle condition on phases we saw in the lower dimension. There's this extra term VG because omega is now an operator, not a phase, so we can't just pull it out of here and have cancellation between VG and VG inverse. Okay, so we had these omega GH satisfying something that kind of looks like a 2 cocycle condition. But if we take that and we restrict it from the boundary of the region M, which consists of 2 sites, to just one of those sites, call it A, the restriction now only has to obey this previous relation up to a phase. And this phase, I'm again calling omega, it now has 3 arguments, GHK, because the last relation did. And I won't go through all the details, but further analysis shows that this omega is a 3 cocycle. So it satisfies this condition here. And it's only defined up to a 3 co-boundary, delta beta. So we conclude that there's an invariant, which is the cohomology class of omega. And so that takes values in the 3rd cohomology of G.
I'm sorry, in this argument and the previous one, it's not necessary to assume that you have a description in terms of matrix product states.
It's not assumed.
No, I mean, if you have, then for you it's more natural because you know matrix product states, but it's not necessary, right?
It's not necessary.
Okay.
Right. So let's see, oops. Yeah, so this argument from here, here, and here, none of this assumes matrix product
Right.
states. Alternatively, you can argue
Okay.
the same thing using matrix product states, and it's, I don't know, it's kind of nice to see that the invariant happens locally on a single site and the entanglement around a single site instead of having to think about boundaries. But
Yeah.
it's not necessary to use this argument.
Yeah, but the next slide, you do have this VG floating around. So it looks like the next argument requires this picture with the matrix product states, or I'm wrong.
This is maybe bad notation on my part, but VG is just the name I'm giving to the action of the symmetry on the entire boundary.
Okay, so this VG is not the previous VG.
No.
Okay.
Yeah. I mean, yes, yeah. So yeah, that's exactly what I was going to say. So, so so VG was the action of the symmetry on the boundary. If the boundary had made sense as its own system without being attached to a bulk, then the argument would have just played out like in the one-dimensional case. But instead, we got a 3 cocycle, which shows that the boundary has some property which only makes sense if it's attached to this higher dimensional bulk.
Okay.
So that's precisely an anomaly.
Okay. Thanks.
Maybe here's a good place to take a break.
So we have a 10 minutes break, but there is a question first.
I'm wondering, can group cohomology also see the fractionalization in a higher order topological phases? I mean, if I go to the boundary of the boundary, can your anomaly, boundary anomaly see this higher order fractionalization, or it just this something for first order topological system? Is there any way?
I don't know the answer to that. Yeah.
Okay.
Yeah.
And when you say this topology, SPT beyond group cohomology, do you mean because there is a gravitational anomaly there, or
Right.
is just because that?
So that,
or there is something deeper?
It's either a gravitational anomaly or
Yeah.
a mixed gauge gravitational
I see.
anomaly.
Okay.
And that's what I'll start with as soon as we get back from the
Okay.
break.
Okay. Thank you.
Okay, so we have something like 10 minutes break, okay?
Okay. All right, I'll jump back into it. Okay. So actually, before I get to beyond group cohomology, I missed one slide. So just like in 1D, in 2D, there's an alternate argument for tensor networks, and this one's a lot more complicated. I just have one slide on it, and I don't expect us to understand the argument, but I put it here with a reference to just give a little taste of how it works. So now when one acts on the physical leg of the PEPS tensor, the result is something on the virtual legs, once again, just like with the MPS, except now it's this loop. So it's these red tensors, which have 2 of these black virtual legs, but now they also have 2 red virtual legs, and they wrap around the site. Now, if you take these tensors BG, and now you try to compose them together, so you have the B for a symmetry G, B for a symmetry H, and B for a symmetry HG. They have to be related somehow. It's like merging 2 of these red lines together, and they're related by these tensors in purple, which I call X, GH, and they kind of play the role of omega A. You can just look at properties of these tensors X and extract a 3 cocycle from them. So that's just a taste of how it works with PEPs. Okay, so I've talked about cohomology SPT phases, and I want to take us into beyond cohomology SPT phases. In order to do that, we need to introduce the concept of decorated domain wall constructions. And this is just a rough idea. So the rough idea is to build a d-dimensional, let's say G cross H SPT phase out of a d-1 dimensional H SPT phase. So the procedure is to start in a G broken phase. So there's only an H symmetry left. And in this phase, the states are like configurations of G domain walls. So that's what I've drawn here. Now, if we proliferate the domain walls, this restores the G symmetry. By proliferate, I mean, well, there's a way to do it with the Hamiltonian, but in terms of the ground state, I mean, we're taking a superposition of all domain wall configurations. Okay, so that would restore the G symmetry and we'd get some G cross H symmetric phase. But what if before proliferating, one decorates the domain walls with an H SPT? And by decorating, I mean just coupling degrees of freedom to the domain walls such that they have this lower dimensional SPT. Then when one does that, the result is actually an SPT for symmetry G cross H in dimension D. So there's a way to see where this appears in the classification of SPT phases. So if we take the full classification H cohomology of G cross H, Kuhn's theorem splits it up into these pieces. So one of the pieces is just a top level H SPT where G isn't playing any role. The next piece looks like this. So let's look at the coefficients of this cohomology are some H SPT and 1 lower dimension. And H1 of G with those coefficients is telling us that how we assign these lower dimensional SPT phases to G domain walls. So all these phases that come from the construction fit naturally into the full group of SPT phases. And they're actually higher order terms as well, which I'll talk about on the next slide. But before going there, let's look at how the edge physics works, because there's always an interpretation of these invertible phases in terms of the edge. So the H SPT that lived on these domains, when it terminates at the boundary of this higher dimensional phase, it has some edge anomaly, some degrees of freedom that are projected by a projective representation. So you have a bunch of these red edge modes, but then when the domain walls are proliferated, they go everywhere on the boundary, and one ends up with anomalous boundary physics on the higher dimensional phase as well. Okay, so the original domain wall construction worked like that, where symmetry G was actually just Z2, but it's since been generalized quite extensively. So in the most general construction, one can decorate not just domain walls, but also junctions of domain walls. So where a G and H domain wall come together and merge into a GH domain wall, for example. At that vertex, you could decorate it with an SPT phase that's of 2 lower dimensions. Doing this it's very technical, and I won't get into it because you have to subject these decorations to a lot of consistency conditions. And that's how you get the other terms in this Kuhn theorem sum. But to go beyond cohomology, one realizes that these defects can be decorated not just with SPTs, but actually with invertible phases more generally. So if you take some phase such as the Kitaev chain, that's non-trivial even without symmetry, and decorates domain walls with Kitaev chains and proliferates those, the result is some SPT phase, but it's not the sort of SPT phase that appeared in the sum on the last slide. It's actually beyond cohomology. So non-SPT decorations give beyond cohomology SPT phases. So speaking of bosonic systems, the lowest dimensional invertible topological order is this E8 phase in 2 dimensions. So it plays a role in 3-dimensional SPT phases. If I have a 3-dimensional system, I can form 2-dimensional domain walls with respect to my symmetry and decorate them with this phase E8, proliferate them to get some new phase in 3D. And it turns out all bosonic SPT phases can be constructed by this sort of procedure. Fermionic phases work similarly. So there's something called the super cohomology classification, which is like the fermionic analog of the cohomology classification. And there one has not just the bosonic SPT layer, but one is also allowed to decorate 0-dimensional defects with 0-dimensional fermionic SPT phases, which is just a complex fermion where the ground state is the occupied or odd state. And then beyond super cohomology means that you're decorating higher dimensional defects to get all the rest of the phases. There's another perspective on beyond cohomology. One doesn't have to use a decorated domain wall construction to understand it. And this is in terms of response theory. So if you think about putting your system on some space and subjecting it to some background gauge field, then measuring how it responds, there are kind of 3 things that can happen. One, the response can be just a function of that background gauge field. So for example, in 3+1 dimensions, your response could be this F squared term. That's a pure gauge response. It's a cohomology SPT sort of response, but you could also have a system that doesn't respond at all to the gauge field, but responds to the topology of the space that you put it on. So here I've written W2 squared. W2 is something called a Stiefel-Whitney class, which is, it's sort of like a 2-form gauge field, but not for the gauge bundle, but for the tangent bundle of the space. So it's detecting some geometry of the space-time. So if the response looks like that, it's just a gravitational term. And beyond cohomology, SPT phases are kind of in between. They're still SPT phases in that you need to have a contribution from the gauge piece. You need an F. If F goes away, it's trivial. Yet in its construction, these lower dimensional invertible pieces were involved. So it's a mixed response. For example, W2F. Okay, so a nice example to see all of this working in practice is fermionic invertible phases in 1 dimension. So first, let's not have symmetry and just look at invertible topological orders. As I've said before, in 0 dimensions, there's a Z2 classification, there's the trivial phase, and then there's the non-trivial phase, which can be modeled with a complex fermion with odd ground state, so occupied ground state. In 1 dimension, there's the Kitaev-Majorana chain. Okay, now let's add symmetries and build SPTs out of them. There are 3 invariants. One of them is this top layer, which is just bosonic SPT, doesn't care about fermions and fermionic phases at all. There's a next layer B, which is the mixed layer. So one looks at G domain walls and decorates them by these 0-dimensional phases, the complex fermions. And then there's a 3rd layer, which it doesn't care about the symmetry and is just this invertible topological order of fermions. So the SPT phases are the phases where you don't have this 3rd layer, so gamma equals 0, and they all belong to super cohomology because the only thing we're decorating with are 0-dimensional phases. And these have the different types of anomalies on the boundary that I talked about on the last slide. Alpha encodes the projectivity of the boundary action G, so it only has to do with the group. Beta is a little more complicated when gamma equals 1, but at least when gamma equals 0, it encodes whether your symmetry action VG is parity odd on the boundary. So in the bulk, at least, your symmetry action should always commute with fermion parity. Otherwise, you have supersymmetry. You have symmetry that's mapping bosons to fermions and vice versa. But on the boundary, a signature of that mixed anomaly is that VG might not commute with fermion parity. And then the gamma equals 1 phases have these dangling Majorana modes, which is a gravitational anomaly. On the lattice, what it looks like is that the boundary Hilbert space is not really defined. Like you could have a Hilbert space on the boundary, but the space of operators that the system defines on that Hilbert space is not the full space of operators. You only have 1 Majorana there instead of the pair of Majoranas. Okay. We just had some questions, but is there another quick question before I go on? Yeah.
So
yeah.
In the response theory, you had the Stiefel-Whitney class. Are there other topological classes you can use, or why is the Stiefel-Whitney special? I mean, it's because of the fermions? Or?
So the Stiefel-Whitney class, I guess the terms that can appear are the cobordism invariants. So the bosonic cobordism group is generated by Stiefel-Whitney classes, and in 4 dimensions, you have this additional Pontryagin class. So those are the terms that can appear. For fermions, you have W2 or second Stiefel-Whitney class is trivial because you need to have a spin structure, but you can write down other terms. Like W1 still makes sense, but there are things like the eta invariants, the ARF invariants. Yeah. Cool. Okay, so to put this next section in context, so far we've characterized phases, but we haven't really given a procedure to detect them. I guess if you have access to the boundary and you can directly measure the anomaly, then do that. But it'd be nice if there was some way, just looking at the bulk of your system, that you could tell you're in a non-trivial phase. And at first glance, you might say, no, that's impossible. You don't have any bulk anion excitations. The bulk is almost trivial. So how could you distinguish the phase from the trivial phase in the bulk? But it turns out it's possible. So to do that requires order parameters. So under the old Landau paradigm, phases were characterized by patterns of symmetry breaking. And the way to tell how the symmetry was broken was to take some operator, symmetry breaking order parameter, that transformed a non-trivial representation of the symmetry And if it picked up a non-zero expectation value in the ground state, that would mean that the symmetry is broken. So you're in an ordered phase. The same idea works for invertible phases, except now, since they're locally indistinguishable from product states, one needs to use an order parameter that is not local. So it's not defined at a single site, but rather some extended region. So I think the best example to start with is string operators in one dimension. So let's take the symmetry group G to be abelian because it makes things a lot easier. What a string operator is what I've drawn here. So there's a string of length should be large, like larger than the correlation length. It should be larger than the number of times you need to block your MPS to make it to get to a fixed point. But you have a bunch of UGs, action of the symmetry, in the bulk of the string. And then at the end of the string, you're acting with some operator O alpha. So these end operators are just any operator that transforms in some representation alpha of the symmetry. Since it's abelian, it's just a linear character. So the expectation values display a pattern of zeros. So if I act on a state characterized by some invariant omega with the string operator, I will get a zero expectation value unless this relation between the SPT invariant omega and this character chi alpha is satisfied. So this ends up, if we have these pattern of zeros for all values of G and alpha, this determines the ratio omega over omega, and that ends up determining the full SPT order. I was going to give an argument of how this works with matrix product states, but I think in the interest of time, I'll skip through the argument. You'll just have to trust me, but the slides will be available online. Okay. Okay, I will also skip through this slide, but what I'm saying here is that one has this ratio omega over omega that was extracted from the string order parameter, and one can use it to determine the cohomology class of omega uniquely. So the SPT invariant is detected just by these expectation values of strings. Okay, but there's another picture of string operators. So one can form twisted sector states. So take I'm going to write it as an MPS, but I think this makes sense without MPS. Take the MPS state and insert the action of the virtual symmetry H on the virtual level, so it just gets slipped into the trace. Alternatively, you take a ground state of some twisted Hamiltonian. So that's like the Hamiltonian on a loop with a flux inserted through the loop. Now act with the symmetry UG on that twisted sector state. If you just follow through the algebra using the relations that the MPS tensors have, you get out that the charge of the state is exactly this ratio omega over omega. So we've recovered exactly the data that string order parameters captured just by taking twisted sector states and looking at their charges. In space-time, this has like a nice picture. If the space is basically this loop that has a G, that has an H domain wall on it. And when we take the G charge, that's like filling out the time circle, but there's a G domain wall in the cutting across the space direction. So we get a torus with fluxes G and H on its two cycles. And when those G and H domain walls have to intersect each other, and when you split them up into two trivalent vertices, each of them gets a weight omega over omega, and that's where the ratio omega over omega is coming. So basically the SPT order is detected by these torus partition functions. Another more exotic example is partial inversion operator, which came, yeah.
I didn't get the previous argument. You are saying that in this case, the ground state is non-degenerate on the torus, right?
The
In
gra-
absence of twist, the ground state is non-degenerate,
It's
right?
non-degenerate. And then also once you twist it, that ground state is also non-degenerate. In each twisted sector, there's one ground state.
Okay.
And then I'm just looking at the charges of these single ground states. So,
So this is just twisted boundary conditions.
yes.
Okay.
Yeah.
Okay.
So yeah, for each group element, I get a different twisted boundary condition, and then I'm taking the charge of the state that lives with that twisted boundary condition. And the collection of all that data ends up determining the SPT order. Yeah. And none of this used boundaries or anything. It was a purely bulk method of detecting the SPT order. Okay, so for something more exotic, consider the partial inversion operator, which I think came up in last week's review talk. This is used to detect reflection invariant SPT phases, which are a bit beyond the scope of what I talked about so far. I've been focusing on on-site symmetries. But there are two reflection invariant phases in one dimension. And to distinguish them, one acts trivially on the sides of the system, but on some region in the middle of the system, one performs a partial inversion. So just reverse the order of the sites. Diagrammatically, it looks like this. And the expectation value of this thing, if one takes its sign, it can be positive or negative. And that tells you whether you're in the trivial or non-trivial SPT phase for inversion symmetry. So these are just examples, but I want to put them in more of a unified framework. And to do that, we use TQFT. So a TQFT is the effective QFT that you get when you have a gap. If you have a gap, the physics at long distances is just the physics of the ground state, and the physics of just a ground state is a topological field theory. So a TQFT is a space-time thing. So it basically eats space-times with spatial boundaries, and then it will return the maps or the partition functions that it assigns to those space-times. Another interpretation is that the TQFT is encoding responses to gauge and gravitational probes. So for an example of how this works, well, we already had one, the partition function of some TQFT on this torus twisted by G and H is this omega over omega that captures the SPT order. Another example is the ground state degeneracy on a space. This is it for some possibly topologically ordered state where there is ground state degeneracy. You get the ground state degeneracy by taking the path integral of the cylinder of that space. So it's the space times S1. The TQFT computation just spits out, that's the trace of the identity map on the space of ground states of that space. So you just get the dimension of the Hilbert space. One can do similar things with fermionic systems, try to encode properties of the system in partition functions. So for a fermionic system, the boundary conditions satisfied by the fermions amount to what's called a spin structure. So essentially around each cycle, you can have periodic or anti-periodic boundary conditions, and they have to satisfy some slightly non-trivial consistency conditions between them. So just as a gapped bosonic system has an effective theory, which is a TQFT, a gapped fermionic system produces a spin TQFT. So in a spin TQFT, we have order parameters. So just like the cylinder of a space gives you the ground state degeneracy, the cylinder of a space where I've put periodic boundary conditions in the time direction spits out something else, which is the number of states that are bosonic minus the number of states that are fermionic. one can keep adding richer and richer structure. So if we add a time reversal symmetry, that means that the theory is insensitive to the orientation of space-time. Like reversing the direction of time flips the orientation of space-time, but if that's a symmetry of our system doesn't care about space-time orientation. So it means that the theory can actually be defined on space-times that don't have an orientation. They're non-orientable. So a gapped bosonic system with a time reversal system gives you an unoriented TQFT. If you have fermions and time reversal symmetry, you get kind of an unoriented version of spin, which is called pin. Okay, but you can also get order parameters out of partition functions of these unoriented theories. So this partial inversion operator, which I just told you about, well, partial inversion, well, it's an order parameter for reflection symmetry, and reflection symmetry also reverses the orientation of space-time. So it should have something to do with unoriented TQFT. It turns out it can also be realized as a partition function in the TQFT. It's the partition function of a space called RP2, which is unorientable. The way to see that is to realize that RP2 can be built by taking a space and then adding a crosscap to it. A crosscap basically means we cut out a disk and then we glue the boundary of the disk together using the antipodal map. So we glue opposite points to each other. And that's like exactly what's happening over here with this order parameter. So if one squints, one can see that the expectation value of this order parameter looks a lot like this partition function on an unorientable space. Yes, and one can go further and talk about higher dimensional invariants, such as the phases that we know to exist in the interacting periodic table. And it turns out that many of them, the order parameters have been realized in terms of topological partition functions. And actually, since we're dealing with unitary theories and theories that are invertible, they're completely determined by closed space-time partition functions. So you never have to consider space-times with boundaries. So if one believes that the TQFT constitutes the same data as the lattice system that you started with, or the long distance physics of the lattice system you started with, in principle, all of the order parameters should be encoded somehow in topological partition functions of the TQFT. Yeah.
As opposed to what? Unitary as opposed to what? You mean non-emission Hamiltonians?
Yeah, exactly. Yeah, just like normal quantum mechanics. Yeah. Okay. So any questions on this before I just go super fast through this last section? Okay. So this is these are some slides that I added just last night after hearing this nice introduction on the tenfold way by Christopher yesterday. So I thought, since I'm talking about interacting invertible phases, while at the same time systems of free fermions are non-interacting invertible phases, and they have their classification, it'd be worth discussing the relationship between the two classifications. So free and interacting fermion systems, the setting is a lattice where on each site we have this Fock space built out of these fermion operators. J is the site of the lattice. A is some flavor index for the fermion. You can have different types of fermions on the site. So generically, a free fermion system looks like this on the left. So there's a hopping term, there's like a superconducting term, and that's all you can write quadratically. Interacting fermion system is simply adding to this Hamiltonian additional terms which are higher order. So the question one could ask is, what's the classification of free fermion phases with the symmetry G, and how does it relate to the interacting classification? So here's a diagram of what can happen. So let's say we take this space of free fermionic systems. Everything in this gray box is free fermionic systems. And let's say the gapped ones are these blue regions, like the gapped symmetric ones are these blue regions. So it naturally splits up into a few different phases. So system A is topologically trivial because it's connected by a path to the trivial phase, whereas systems B and C are non-trivial. But now we embed the space of free systems into the larger space of interacting systems, and a few things can happen. Now A becomes connected to B, so B is now trivialized. Also, we have this phase D over here, which we couldn't even see when we were dealing with just free fermions. It's intrinsically interacting. So the names we'll give these are unstable free phase because it's destabilized by interactions, and an intrinsically interacting phase. So to see this working, let's consider the famous example of Fitkowski and Kitaev. So we're in one dimension. We have these fermions, and it's useful to write them in a basis of real fermions or Majorana fermions. Let's suppose we impose a time reversal symmetry that acts on the fermions like this: squares to 1, takes A to minus A. And we're interested in translation invariant quadratic Hamiltonians. And there are basically two types of terms you can write. You can couple the Majorana on 2j minus 1 to the one on 2j, and you can couple 2j to 2j plus 1. U and V are just parameters. And we're interested in values of these parameters such that this total Hamiltonian H is gapped and time reversal symmetric. So in this free fermion language, everything I said about ancillas carries over. So when you tensor by an ancilla system, that's just adding to the, adding a trivial system by a direct sum to the band space. An ancilla system in these variables is just given by this Hamiltonian here. It just, all it does is project on each site to some state 0. So its ground state is a product state. And to define phases, we're interested in adding ancillas to systems and then deforming them while preserving the gap in the symmetry. So Fitkowski and Kitaev noticed that there is this phase with Hamiltonian H1 that is not connected by this phase relation to the ancilla system. So it's in a non-trivial phase. And actually you get a bunch of them, you get infinitely many of them by stacking multiple copies. So for each natural number n, you can take that many copies of it. I think it's actually more appropriate to think of the integers rather than the natural numbers, because one cares about boundaries between phases, which are like difference classes on the phases on the two sides of the boundary. So one has infinitely many free phases. Okay, but now consider turning on interactions. It turns out that in this larger parameter space, phase number 8 is destabilized, so it's connected to phase number 0. So the classification goes from integers to integers mod 8. So in this diagram here, like B would be phase number 8. It was non-trivial in the set of free systems, but there's a path that passes through the interacting parameter space that connects it to trivial. And I'll mention that T symmetry is important here. If you don't have it, you just get a Z2 classification, whether there are interactions or not. Okay, so this can also be understood in terms of invariance. So one-dimensional phases of free fermions with the symmetry are classified by a single Z invariant that you could read off of this periodic table of topological insulators. The physical meaning of this invariant is the number of dangling Majorana modes. So I said earlier in answer to a question that pairs of dangling modes can be gapped out together, but if you have a time reversal symmetry, there is no time reversal symmetric interaction that gaps out pairs. You can just keep adding dangling modes and you can't get rid of them. But if you allow yourself not just quadratic interactions, but higher order interactions, there are time reversal invariant interactions that can gap out several modes, except you have to wait until you get 8 of them. So at order 8, the dangling modes are gapped out by interactions. Okay, so let's put this in the context of other phases. So it fits into K theory. This Z appears on the periodic table. I guess it's this one here. So class BDI, that's T squared equals 1 in 1 dimension. So there's a Z. And the Z8 appears here in the interacting periodic table. And this is just a snippet of what I showed like many slides back of the conjectured classification of interacting phases. So you see that there are many other examples like this where you have some Z in the free case, but it collapses to some smaller set of phases in the interacting case. Like in 3 dimensions in class D3, your Z collapses to a Z16. So these are examples of destabilized free phases. But one also gets more exotic things, which I've noted in blue. So here there are more interacting phases than there were free phases. So that indicates new intrinsically interacting phases. So you see them, for example, in 6 dimensions with class D, you get a Z squared instead of Z. That's kind of like not relevant for condensed matter physics because it's in 6 dimensions. However, what's interesting is that if one imposes symmetries, one sees these intrinsically interacting phases even in low physical dimensions. So there are some examples given with crystalline symmetries. In 1 dimension? Oh, yes, in 1 dimension with symmetries, you do get examples. Yeah. Let's see. Yeah, off the top of my head, like I think, so you have this SPT phases in 1 dimension are characterized by this 2 cocycle omega. Already, if omega is not Z2 valued, so if it takes advantage of the full U1 instead of just taking values as plus or minus 1, then I think that already tells you it can't have come from a system of free fermions. But the argument for that is in this last reference. Yeah. Okay. So.
Sorry, can you go backward?
Yeah.
What are these symbols K, O,
Yeah.
not Z and home, Tors, and so on?
So I didn't explain this at all. This is just this is a hieroglyph that represents K theory. So the meaning of all these entries in the periodic table and how they were computed is K theory. The meaning, everything over here is computed from something that's related to cobordism. So the omega is like a cobordism group and you do some things to it and what comes out is the entry in the table. Yeah, so I was just, this particular thing, so KO0 as opposed to KO some other n is Z. That's where the free phase is. This particular thing, 2, the subscript 2 is for dimension 2. Pin minus means that I have a time reversal symmetry squaring to +1 and I have fermions. That's mathematically what class BDI looks like in terms of interacting phases, and that computation spits out a Z8.
Account for the Z8 on the table, on the right table.
Yep,
Okay.
it's this Z8.
Mm-hmm.
Yeah. Yep, and everything else in this table is like this sort of thing, which I didn't explain at all, but with different subscript and superscript on this omega. Yeah. Okay, so that's about time. So let me just recap what we did, because we kind of took a long and winding journey through several tenuously related topics. First, we talked about entanglement structure of gap states, and that enabled us to use tensor networks, which at least I thought gives an interesting perspective on some of the arguments we encountered later on. Then we talked about invertible phases, and I gave you a lot of definitions. We talked about stacking and how some gapped phases are invertible under stacking, and these include all SPT phases. Invertible phases are characterized by the anomalies of their boundaries. So for a large class of them, that anomaly is captured by group cohomology, and we saw several arguments about how that appears when one looks for anomalous behavior of the boundary. Then we talked about beyond cohomology SPT phases, how they come from decorated domain wall constructions and how they have mixed or gravitational anomalies. The second to last section was on invertible phases, how they're distinguished by non-local order parameters such as string operators, and how these are closely related to topological partition functions. And finally, I told you about the free and interacting invertible phase classifications and how exotic phenomena like unstable free phases and intrinsically interacting phases exist. So I'll stop here and happy to answer any questions.
Okay, thank you very much. So the fractional Hall effect is not included in your analysis.
Correct, because it is non-invertible.
Mm-hmm.
The integer quantum Hall effect is included. It's an invertible topological phase.
So why is that invertible so important for you? Because in terms of anomalies, for example, fractional and integer effect are just the same. I mean, just the same.
Right. I mean, I think the invertible phases are interesting because they basically are the anomaly and nothing more.
Okay.
Yeah.
So what's the status on the Hamiltonian formulations for these things? Since they're all unitary, they should exist. Each of them should have a Hamiltonian, but what is known about them?
Yeah, I think all of these up to 3 dimensions at least have Hamiltonians.
I mean, are they explicitly constructible or?
Yeah.
Okay.
I'm like 90% sure that's the case. I think the.
I mean, I know various papers which do construct some subsets of this. I just don't know how extensive these constructions are.
Okay. And if it's chiral in 2 dimensions, then it's complicated. But yeah, for non-chiral things, I think they exist.
Okay, thanks.
Sorry, maybe how do you cancel normally such invertible anomalies? What is a standard technique for it?
So basically, an anomaly means that it's a property of a system that suggests that it can't live on its own. It needs to live on a bulk of on the boundary of a higher dimensional system. So the anomalous behavior of the boundary is canceled by its presence on the bulk. So yeah, for example, maybe you have some like field theory action of the boundary and has some gauge non-invariance, but the bulk also has a gauge non-invariance that's localized to its boundary. So when you put them together, you get something that's gauge invariant as a whole. That'd be an example.
Thanks.
So I have a quick question.
Go ahead. Go ahead.
Thank you. Yeah, so the topological partition function, so they will compute some topological invariant of the manifold. So are there cases in which it depends on the geometry of the manifold, not just the topological class?
Yeah, yeah. So for these chiral phases, which they demonstrate a thermal Hall conductance on the boundary. The way to see that from partition functions is subtle. So the TQFTs are not true TQFTs. They're theories with a framing anomaly. So I think the way that you would see the central charge is to take the 3-sphere with some framing on it, and the partition function of the non-trivially framed 3-sphere would give you the central charge. So I think that's the only way that some geometry beyond topology crops up.
Okay, thank you.
Can I ask a question?
Yes, yes.
So the free invertible phase classification was discussed, and I believe that in the field theory limit, this corresponds to something like, okay, this corresponds to Dirac fermions with various mass terms. And I'm wondering if we consider something like the gravitino, or the Rarita-Schwinger field. So the fermions, which are spinors, but also with vector indices like mu, nu, rho. So if we consider fermions with such space-time indices, do we get more possibilities? Do we get more phases that are not covered in the standard free fermion classification?
The audio is really muffled. I missed that. Did anyone?
I think he's saying that in principle, if you have a fermionic system, there is not only the gravitational the gravity, but also the gravitino. So in principle, there is some other background beyond gravitational background.
Not background. I'm concerned gravitino as a fermion.
So I miss your point. Can you repeat it?
Okay, gravitino is a fermion. So I want to replace the Dirac fermion by the gravitino or something more general. And then I suppose we can try to give a mass. And I'm wondering if we get a new phase, if we get new phases that are not covered by the standard free fermion classification.
I'm not sure I'm completely understanding. Are you in like electrons? You have a gravitino, phases of gravity. I don't know. Do gravitinos do spin structures?
Yeah.
Just a same spin structure as electrons. All of this applies to them.
Yeah. What is special about gravitino? It's still a fermion.
Yeah, but it has a more non-trivial coupling to the gravitational background.
Ah, I see. Like that, you're wondering whether there are more exotic gravitational anomalies. Ah, I'm not sure. I guess the way that gravity is appearing and what I talked about is not like dynamical gravity. You have some, it's like a background field. So in the same way,
I understand.
Yeah.
Okay, thank you.
So I would like to understand better the gravitational anomaly for interacting SPTs, because you have this non-orientable manifold, right? And as you said in one of the previous slides, so you have this second Stiefel-Whitney invariant just because that is a topological obstruction to the spin structure, right?
Right.
But you know, on non-orientable manifold, there is also the first Stiefel-Whitney, which is an obstruction to the orientability. So I guess they should appear, right? The first Stiefel-Whitney in interacting SPTs, right? On when you look at the gravitational anomaly, is it correct?
Yeah, that's correct. And so I had that list of responses before. W1 to the fourth should have appeared there. F times W1 squared should have appeared there. I left those out because the names of them are complicated. Like even though W1 is a gravitational thing, it's also like the gauge field for time reversal symmetry. So it normally counts as in cohomology. Yeah.
Okay.
But yes, those are other responses that systems could have.
And then just as another small question, I guess in higher dimension, you will get even the fourth Stiefel-Whitney, I mean, on RP4, let's say, on something that in higher dimension you would go up in the Stiefel-Whitney class, right?
Yep. And then there are relations between the Stiefel-Whitney classes. So in 4 dimensions, W1 squared, W1 to the fourth plus W2 squared equals W4. So that would not be an independent invariant.
Yeah, because you have the Pontryagin also there.
Right. Yeah. Not if you have time reversal, but if you get rid of time reversal, then you have like the gravitational theta angle, which is the Pontryagin class.
Yeah. Thank you. Thank you.
So a physical picture for these W's is this decoration of domain walls, right? That was your point, right?
The physical picture of
for these W's, for this Stiefel-Whitney thing, was the decoration.
Yeah, right.
In the decoration of the domain walls.
Right.
Mm-hmm.
So, right, like if you put like in 1+1 dimension, there's a non-trivial time reversal symmetric phase. It has partition function W1 squared. So one could put these sorts of things in a decorated domain wall construction.
Mm-hmm. Okay, so if there are no more questions, I think we thank the speaker again. And that's it for today. Okay, goodbye to everybody. See you.